Hey, everybody. So I got a couple questions about this homework question, so I wanted to go through it. And I'll first acknowledge that this is, I think, one of the ones that had some technical difficulties, and so I've been messing with it, and it's actually kind of an incomplete problem right now. It doesn't give you an alpha, for instance, but we don't need what's missing to complete this. So I think it's worth going over. All that's expected is that we compute the p-value, right? The last step of a hypothesis test would be to compare the p-value to alpha, so we can't do that. I'm having some issues with how it's accepting answers, and so I've just kind of shut that part down for now. But let's go ahead through the setup anyhow, so we can get a sense of how this would work out. So there's a lot going on in this problem. And so one of our first jobs is to read through and determine what's important. And so we've got this company that harvests trees, and we add, there's a treatment in question here that we're trying to decide if we want to pay for, okay? And so there's data that with the treatment, oops, let me get a bigger pen here, make this whole thing a little bigger. That with the treatment, the mean height of 4-month-old trees is, where do we have it? 55.4 centimeters. And so what we're trying to decide is if we should pay for this service. This is with the treatment, if we want to pay for this. And so we're going to assume that the treatment has no effect. In other words, let me say this a little more clearly. H naught for trees without the treatment, we're going to compare this to trees without the treatment. We're going to assume that they have the same mean, okay? That there's actually no effect by removing this treatment. And our alternative hypothesis is that this will make the mean actually less, right? That's our setup here, okay? And so the problem goes on to talk about collecting data, getting a sample mean of trees without without the treatment of getting a sample mean of 52.9 centimeters. This is for a sample of size 19. This sample, we're also told, has a standard deviation of 6.6 centimeters. And so it asks us to do a hypothesis test, but like I said, because of some technical issues, all that we're really expected to do right now is calculate the p-value, okay? So remember what a p-value is. The p-value is, what is the probability of getting a sample like the one we got, in this case at 52.9, or more extreme, if the null hypothesis is true. So getting a sample as extreme or more extreme than the one that we got, okay? So let's do a little picture of this, right? This is going to be, we're going to use the student's t-distribution in this case. We're in that case where we don't know the population standard deviation, but we do know it for the sample. But a student's t-distribution looks almost precisely like a normal curve, right? To the naked eye, they're identical. In reality, there are differences. For lower numbers of sample size, the differences get larger. But to the naked eye, it's a bell-shaped curve. Okay, same look to it. And so for the purpose of understanding the problem, we can just do the same sketch, right? And it's the same idea, right? Remember, the standard normal curve is made up of z-scores with a mean of 0. Our t-distribution is made up of t-scores with a mean of 0. And so our question is, if we get this sample, we can convert this to a t-score, and we're going to ask ourselves, what's the probability of getting that t-score? So I'm going to mark this as the t-score for 52.9. We still have to compute this number, and then we want to know what is the area below it, because that would be the probability. That red area would be the probability of getting a t-score at or below the t-score for our value, okay? This is our p-value, right? Whatever this number turns out to be, that's the idea. So let's go ahead and do this. We have all the information that we need here. So our t-score, right, or what I've marked as t of 52.9, is the sample mean minus the mean divided by the sample standard deviation, which is itself divided by the square root of the sample size, right? So one possible issue here, make sure when you are entering this into a calculator, this division happens first, right? Division doesn't commute the way that multiplication does. So we have to be very careful how we enter this, right? You might enter this number first or compute this number first and then divide the difference here. Or if you've got something that lets you put in more symbols, which I'll use in just a moment, you make sure that these have parentheses. So in our case, this is going to be 52.9 minus 55.4 divided by 6.6, which is divided by the square root of 19. Okay, so I'm going to jump over to Desmos. I like this because I can see the entire, I don't have to track any decimals as I go. Every time you write something down, you're rounding a little bit typically. Oops, let's put parentheses in to be clear. 6.6 divided by the square root of 19. Okay, and there we see our answer of negative 1. I'll go out to 5 or 4. Let's go 4 decimal places. 1.6511. That should be enough. And now we need to compute the p-value, which, as I wrote up here, is just, scroll down a little bit. Our p-value is going to be what's the probability of getting a t-score less than or equal to negative 1.6511. And for this, we need a calculator. I've got this one here. Remember, the degrees of freedom is 1 less than the sample size. Our t-score is negative 1.6511. And we get 0.0580. Notice our t, this particular t distribution calculator, and this is one I like to use, is giving us below, right? The problem, it's exactly what we want. If we had a different problem where we were looking at values above, we would have to use this a little differently, right? If we had one of those problems where our null our alternative hypothesis is that the mean is actually larger, we would have to, we'd be looking for an area up here. This calculator would give us the area below to the left of what we wanted. We could subtract it from 1. Or if we were doing a two-tailed test, we would be able to find, we'd have to do a little more thinking, but the same way that we'd have this picture of, right, if our alpha was 0.01, we'd divide that area between the two sides, that sort of thing. So that's the idea.